Cool. Can I get that out of the way for the moment? Okay, so there was a request to take a look at this problem from the homework. And I'm going to talk through like what my thought process would be on this thing. And that's going to start with, is that algebra trig or a mixture of stuff? It's just algebra, which means there's probably a just algebra solution. I know at least 2 just algebra solutions. And I didn't actually look at which one your instructor chose, but it doesn't matter. They're all valid. If I look at that, I'm looking at the powers of x on the top and the bottom. And since they're the same, I know that I could do polynomial long division. I could do polynomial long division on this, and I will if someone really wants me to. There's also a clever mathematician trick that we can use. Also algebra, clever mathematician trick, or polynomial long division. What do people want to see? Clever mathematician trick. Here's the clever mathematician trick. You see how the stuff on the top is almost the same as the stuff on the bottom? What's the only extra thing on the top? So I'm going to rearrange the top to put the x squared plus 1 together and then have this plus x at the back. And the reason that I'm doing that is I'm going to rewrite this as 2 separate fractions. One of those fractions is going to look like x squared plus 1 over x squared plus 1, which is 1. And the other fraction is going to look like x over x squared plus 1. By the way, that's exactly what you would get as a result if you did the polynomial long division. Each of these, I know I can integrate. I can find the antiderivative of each of those. Antiderivative of 1. Oh, actually, let me do one more thing first, which is we're integrating or finding the antiderivative of this whole thing. But anytime I have addition or subtraction, I can break that up into separate pieces. And sometimes that's just easier to see what's happening. So I'm going to go ahead and do that. Because this first piece, I can just straight up integrate. The integral of 1 x plus some constant. Now the antiderivative for this second piece, I'm going to look at that and go, oh, hey, is algebra trig or mixture? It's just algebra. I sure hope the derivative of one part equals the other part, kind of, sort of. So I would do a u substitution on this because that denominator of x squared plus 1 has a derivative of 2x. And while I don't have 2x dx, I have x dx. So if I multiply both sides by 1/2, then I can make the substitution that this is 1/2 du over u. And this is that special integral that we do have to recognize as being equal to the natural log. One of the reasons that I split it up is that our u substitution only applies to this piece. This other part is already done. That x plus c, we're just going to keep bringing along for the ride. This part we're ready to find the antiderivative of. And I would have 1/2 natural log absolute value of u. But I'm going to sub back in the x squared plus 1. And that would be my final answer. I'll pause there for a second in case there are questions about that. Would anyone like to see the polynomial long division just for fun, or should we call that good? We're gonna call that good? Okay, yeah. So thoughts on what we do today? I was thinking that we could definitely practice some more taking an area and writing that as a definite integral. There are also some properties of definite integrals that like involving even and odd functions, involving splitting up areas into different parts that I thought we could take a look at also, but I am open to working through more homework problems as well. So are there any other questions from homework 10 that someone really wanted to take a look at specifically? Yeah.
I have a question about number 2.
Okay. So I'm looking at number 2, part 2. Okay. And number 2, part 2 from homework 10 looks like we want the region bound by y equals x squared plus 4 over x from x equals 1 to 3 and the x axis. So I think the first thing that I will say is if you're working on a homework problem and it would help you to see what the graph looks like, then by all means, throw that into Desmos and see what that looks like. We don't technically need to do that. I am a huge fan of fake graphs. Here's what I mean. Here's my fake graph. Well, what really is important for finding the area between something and the x-axis is I would like to know when it crosses the x-axis. And that's kind of the only thing that I really need to know, because I want to know, is it above the axis or below the axis? But if I tried to set that equal to 0, x squared plus 4 is never 0. This doesn't cross the x-axis. So I don't really care what it looks like. I know that I'm looking for the area from 1 to 3 of whatever. Also, I know that it's positive because the top is always a positive number, something squared plus 4, and the bottom is positive at least between 1 and 3. So I just need a fake graph, or a fake graph is sometimes helpful, would be a more accurate thing to say, I suppose. So if I were setting this up as an integral, I'm saying, okay, my area comes from the function times a little bit of base, which is dx for my arbitrary cross section here. And I'm integrating from 1 to 3. Now, if all I had to do was to set this up, I don't know where that extra thing came from, then I'm done. But if I need to actually evaluate this and get to an area, now I'm falling into that 2-step process from the fundamental theorem. I need to find the antiderivative and then plug in the endpoints. Well, when I walk up to this, I can see that it's just algebra. If I can make this look like x is raised to powers, I probably should. You could do this as polynomial long division, but we don't have to because there's just one term on the bottom. And because I just have one term, I would choose to break this apart to say x squared over x plus 4 over x. I don't know why I'm bending down. The table moves. Okay. Yeah,
So we don't have to break it apart. It's more of like a preferred.
I don't know how else to integrate it. So the only two options that I have are to do long division or to break it apart. I got nothing else. So this is the route I'm going to avoid long division. Well, x squared over x simplifies to just be x. And I'm going to leave that 4 over x. I'm just going to write it as 4 times 1 over x. Now I'm ready to find the antiderivative, plug in the points. So when I take the antiderivative of x, I'm going to get 1/2 x squared. When I take the antiderivative here, that 1 over x dx or 1 over u du, we have to recognize that that's natural log. So that's going to look like 4 natural log. Now, technically we should have absolute values, but I can already see that we're plugging in a 1 and a 3. So they're going to be positive. So I'm just going to write it as ln of x. Again, we're going 1 to 3. By the way, we read this as 1 to 3, but when we do the subtraction, it's always the top number minus the bottom number. So when I plug in 3, I've got 1/2 of 9 plus 4 ln 3 minus, and I'll put it in parentheses. When I plug in a 1, I'll just have a 1/2. Natural log of 1 is one of those special numbers. What's the natural log of 1? Cool, it's 0. That's one that you definitely want to like keep in your back pocket because it can often help to simplify a problem. So the natural log of 1 is equal to 0. The natural log of e is equal to 1. E to the 0 is equal to 1, and e to the 1 is equal to e. I would say all of those are things just to kind of keep fresh in your memory. And I have noticed for sure on the solutions for the homeworks, anytime there's an ln of 1, he's just like not even writing it because he knows it's going to 0. So if it looks like something's missing in the problem, you might want to check if that's what happens. Can I get rid of this? People are still writing. Okay. So I mentioned that there are some properties associated with our definite integrals and thinking about the fundamental theorem of calculus. And one of them is that if I have some graph, I don't know, sure. I have some graph. One of our properties of the fundamental theorem of calculus, if I'm calling that f of x, and let's say that was a -3 and that's a 0, and just for fun, I'll let that be 4 and I'll let that be 7. Well, if I write the integral of f of x dx from -3 to 0, I didn't actually give us enough information to know what that area is. But we can interpret this. We sometimes talk about the signed area under the curve, or the signed area. If the area between the curve and the x-axis is below the x-axis, we define that to be negative. So if I took this integral, whatever else happens, I know that I should get a negative answer. This will give me a negative number. And the reason that that's happening is that if I think about back to our area is equal to a height times a base. Well, in this case, each of our heights of those rectangles is actually a negative height, right? If I'm using the value of the function to define the height, then it's a negative height for each of those. Other properties of definite integrals. If I were to take that same area, but switch the bounds and say that I'm going from 0 to -3 of f of x dx, this is going to give me a positive number, and it's going to be exactly the negative of -3 to 0 of f of x dx. This one's a little bit harder to sort of rationalize, but I kind of think about this one as saying, well, we know the heights are negative, but this time our bases are also going backwards because we're going from 0 towards -3. So like the base of each rectangle or the width of each rectangle would kind of be like a negative number as well, because we're moving in the negative direction. So overall, this thing would work out to be positive. Question?
For the second, for the integral.
Yep.
Why would it switch to 0 being the up?
So it wouldn't switch on its own, but there are times when numerically it's better for you to switch them. It's also, there's like this whole set of problems in the book that involve manipulating these rules. And this is one of our rules, that if I take the integral from a to b of f of x dx, that's equal to the negative of the integral from b to a of f of x dx. Other properties that are sometimes useful. If I wanted to think about the area in here from 0 to 7, a little bit late. So if I were thinking about that area from 0 to 7 of f of x dx, well, that's the same as if I split this into two pieces and I took the area from 0 to 4 and I added that to the area from 4 to 7. And this idea, that's going to be super critical for us in the next section that we're doing, when we're not just finding the area between a curve and the x-axis, but we're actually finding the areas between two different curves. This property is going to be super useful, that for a definite integral, we can break it up somewhere in between and then add the two separate integrals back together. There are two more like properties of the definite integral that the book gives us in this section, and they have to do with even and odd functions. So can anybody give me, does anyone have a favorite even function? I know it's a really weird question. No one has a favorite even function? Okay, well, mine is y equals x squared. It's my favorite even function. My favorite odd function is sine of x. Just saying. But my favorite even function here is x squared. So one of the properties that is almost never useful, but every calculus textbook seems to think it's really cool, is for even functions. The area from negative a to 0 is equal to the area from 0 to positive a. I like to think of this more as, yeah, obviously, even functions are symmetric. So the area over there should be the same as the area over here. This next one is useful more of the time. I said my favorite odd function was sine, so I guess I got to use it now. So sine of x kind of looks like that, right? There's pi over here. There's negative pi over here. For odd functions, because they're symmetric about the origin, this area over here is the same as this area over here, but remember that our integral can be interpreted as the signed area. So this part down here counts as negative, but it is exactly the same shape as the part up here that counts as positive, which means that for odd functions, if I integrate from negative a to a of f of x dx, I get 0. Now that one's way more useful because if you happen to be staring at an integral of an odd function with symmetric limits, you don't even have to integrate it. We know the answer is 0. And sometimes we can exploit that as a part of working through a problem. Those are like all the properties of the definite integral that our textbook gives us in this section. I hesitate to like do specific problems with it because I'm not sure how much Professor Mock cares about this stuff. I think what would be more beneficial in terms of our time is to practice finding more antiderivatives and applying those fundamental theorems of calculus. I think that's a better use of our time. So, what kind of stuff do you want to practice antiderivatives of? Some trig, some exponentials, some gross algebra, some trig. Let's talk trig. Okay. Let's say that I wanted for us to find the integral from pi over 2 to pi of cosine 3x dx. Do you want me to just let you do it? Do you want to try it on your own? I got a no in the chat. Okay. Those in the room have been saved by Zoom. Okay, let's do it together. So first step, I got to find that antiderivative. So anytime I'm thinking trig, it is helpful to have all those trig derivatives memorized. I'm going to write them all down real quick. You don't have to, but sometimes it's good practice to write things. Derivative of sine is cosine. Derivative of cosine. Negative sine. Derivative of tangent. Secant squared. Derivative of cosecant. I'm doing these in a really random order. Derivative of cosecant is negative cosecant x cotangent x. Derivative of secant is secant x tangent x. And what's missing? Cotangent. Derivative of cotangent is negative cosecant squared x. Okay, these are our derivatives. Those aren't the antiderivatives, but you just go the other direction. So I'm looking at this and asking myself, whose derivative is equal to cosine? Totally, now we got our list. It's got to be sine. I'm going to deal with the 3 by knowing generically what that antiderivative is. If you aren't comfortable with that yet, it's okay to write out the u substitution, though there's kind of a trick to u substitutions when we have a definite integral. I'm going to go with, I already know what this antiderivative is. I know that it has to be 1/3 of sine of 3x. Now, I did notice, I don't know how many of you were active in Piazza, but there have been a lot of questions of like, why the 1/3, right? This is counteracting the chain rule. So if that's supposed to be somebody's derivative, if you had a times 3 out here, then when you took the derivative of this, you'd end up with a 3 times 3. You'd get a 9. So we need a 1/3 out there so that when we take the derivative of this and we do that chain rule, the derivative of 3x is 3, and it cancels out with that 1/3 in the front. If that still feels really uncomfortable, just do the u sub. It's fine. But I'm going to take this from pi over 2 to pi, which means I'm going to get 1/3 sine of 3 pi minus 1/3 sine of 3 pi over 2. Oh, question in the chat. Why is it not negative sine? Yeah, it is annoying. When we take the derivative of cosine, we get negative sine. But we're going backwards right now. So we're looking actually for the thing over here. And so positive cosine comes from the derivative of positive sine. So that's why we don't have a negative here. When we integrate positive sine, that's when we end up with a negative cosine. So it's backwards between antiderivatives and derivatives, which makes sense because antiderivatives and derivatives undo each other. So it makes sense that those signs would be backwards. Cool. I think we should be able to finish this off and actually evaluate. So with like 30 seconds of trig review, unit circle action. Three pi means I started here at 0. I went around the circle to get to 2 pi, and then I kept going another pi. So I'm over here. So my y value is 0. That was really unexciting. Sine of 3 pi is 0. Sine of 3 pi over 2. Well, that says I start here at 0. That's pi over 2, 2 pi's over 2, 3 pi's over 2. So down here, my y value is -1. So that means sine of 3 pi over 2 is equal to -1. And my final answer would be a positive 1/3. Good times. Should we have more fun with trig? Yeah, let's say I've got x secant x squared tangent x squared dx. And I don't know what nice angles might be. Oh, we got stuff squared. I don't even care. We're not going to evaluate this. Let's just do an indefinite integral. I got nothing. You all want to try this one? Yeah, you do. You want to try this one. Give this one a shot. In case it's helpful, I'll bring back the list of derivatives. It's so quiet. You can talk to each other, you know. The masks do not stop sound. I mean, they muffle it a little bit, but.
So the first step, you have to take the
Oh, that's a good question. I don't think you should need to use a trig identity on this. I do think you're gonna want to use substitution, but I don't think you should need a trig identity. And that is a notation thing. So with that 2, we're over here instead. And that 2, we're over here instead. To indicate that it was secant squared, not secant of x squared, then I'm reaching for a trig identity, for sure. Yeah. But for this, no trig identity required. We just need that u substitution. I'm going to let u be equal to x squared. How we doing? Should we finish this off together? So I'm making the u substitution that u is equal to x squared, which means that du is equal to 2x dx. I don't have this. What I have is x dx. So I'm going to manipulate this by dividing both by 2 so that 1/2 du is equal to x dx. This is always my vocabulary list. Sorry, scoot the screen up. This is always my vocabulary list that I'm making my substitutions for. So the x and the dx, they turn into the 1/2 du. And then I'm swapping in for x squared a u. There are other ways to handle a u substitution. I find this in the long run the least likely for students to make mistakes with. So if I keep going forward, secant times tangent is already somebody's derivative. So this will just become secant of u plus a constant. And I'll put back in what u was, which is x squared. Good times. Questions or answers before I move on? Yeah. I don't know how to integrate it. I literally could not integrate it without the x there. So if there wasn't an x there, I couldn't make this u substitution. The only reason that the u substitution is working is because I have the derivative of whatever I'm choosing for u. That derivative can be off by a constant, but if it's off by something other than a constant, it wasn't really a u substitution. There must be some other thing going on. Yeah. But I do want to address, what if the squared wasn't right there and the squared instead was on the secant and the tangent? So let's do that one. So I'm not going to have an x out in front this time because I'm putting my squared in a different place. So I've got secant squared x times tangent squared x dx. And I'm going to look at that and say, oh, well, it's trig. Is it already somebody's derivative? Is whose derivative? Perfect. So I'm looking at this and saying, I see a u substitution in that because secant squared x is already somebody's derivative. So I'm going to come off to the side and build my vocabulary list and say, if I let u be equal to tangent of x, then that derivative is secant squared x dx. Now I've got vocabulary to translate the whole problem. The secant squared and the dx turn into du. That's real nice. And that tangent squared x piece? Well, if u is equal to tangent of x, then u squared would be tangent squared x. Now we're ready to find that antiderivative. I've got 1/3 u cubed plus a constant. And then we'll put that back into x's. So 1/3 tan cubed x plus a constant. Yeah.
Can you explain the difference, just briefly about the difference between when the exponent is for the, above the tangent and above the x?
Yeah, so notation wise. If I write tangent x squared, this means tangent of x squared, like x squared is the angle. But if I write tangent and I put the 2 here, this means that we have tangent of x squared, or tangent x times tangent of x. And it is just that. It is a notation thing. There's like no way that you're supposed to magically know that. Maybe you saw it in a trig class once upon a time. Maybe that was a hot minute ago and you don't remember, but it's a notation thing. Yeah. We've got 7 minutes left. Do we want to do more trig? Are there any other messy ones from homework 10 that anybody would like to look through? Question? Yeah.
Can we do a messy problem where we actually use like the log function, like what I'm doing?
Yeah, sure. I can make up something messy. Okay. Here we go. Okay, this one might be too obvious, but it does look gross. And we can do a more subtle gross one after this. But if you are looking at something really, really gross, you should be hoping there's a U substitution in there. Now, if I were to just think about a U substitution for e to the x, it wouldn't help with the trig. And if I were to just think about a U substitution with the trig, it wouldn't help with the e to the x part. So whatever I'm going to choose, better grab all of it. I really only have 2 choices then. Either the top is somebody's derivative or the bottom is somebody's derivative. Which way is it? And if we do that, right, so this is one where, like I said, I try to make it pretty direct. I'm going to have e to the x, the derivative of negative cosine of x. Oh, I messed up. I meant for that to be a positive sine of x on top. Just pretend it's a plus. Go fix it in your notes. Otherwise you'll look at it later and not know what happened. I stared at that for a long time too, trying to get the sign right. It's hard to work backwards. Well, this is exactly du over u. So this turns into exactly natural log of u plus a constant, or exactly natural log of all of that garbage. Now, times that it's a little bit more subtle. I actually think that sometimes e to the x leads to things that are a little bit more subtle because we tend to forget that the derivative of e to the x is e to the x somehow. So here's one that's definitely subtle. So this is also a u substitution, but if I look at that, it doesn't pop out quite as quickly what the u substitution should be. But I got nothing else to try. So I'm just going to take the piece that's slightly more complicated, that e to the negative x plus 3. Here's where the subtle part comes in. Well, the derivative of that is negative e to the negative x, which I secretly have because I can rewrite e to the negative x as that's like -1 over e to the x. So I have the 1 over e to the x and I have the dx. The only thing I don't have is the minus sign. So this becomes negative du over u. At the risk of confusing things in your notes, if I took that e to the negative x plus 3 and I gave it a power, or I put it inside of a square root, it's no longer a natural log. So if I made that squared, well, now this is really du over u squared. And that's not a natural log. To find that antiderivative, I need to be thinking about that as u to the -2 du. So that I add 1 to the exponent, divide by the new exponent. And I actually think these are the cases that people make more mistakes on, because you kind of get into this habit of 1 over something is going to be natural log, but it's only natural log specifically if it's du over u. If it's du over u to some other power, it's not an ln. I am out of time for today. Tomorrow.